Fractals in Geometry, Fractal Modeling from Nikolaeva and Georgieva, from the High School of Mathematics and Natural Sciences in Bulgaria.
Good morning. My name is Nia, and I'm going to present the topic of fractal modeling. What are fractals? Fractals are self-similar patterns which have no exact dimension. The branching system of trachea tubers, the leaves of our trees, the veins on our hands, river basins, grass, lightnings. All these are fractals. Fractals make us reconsider our notions about the geometrical properties of man-made and natural objects. The underlying reason in studying chaos and fractals is to highlight the objective laws governing all systems which might only appear unpredictable and seemingly chaotic. Such systems are, for instance, weather patterns, turbulent movement of water, the migratory behavior of animals, as well as numerous other aspects of life and nature. It is unthinkable to talk about fractals while ignoring the dynamic processes which have formed them. It turns out that it is a very simple creative process which underlies a very complex development. What fractal dimensions are there, and what are the methods of calculating dimension? As we've already said, a fractal is a self-similar pattern which has no exact dimension. The dimension is a ratio which shows the amount of information needed to describe a particular object. Let's start with the first method of calculating dimension. It uses the property of self-similarity. Let's take a square. It's a two-dimensional plane figure. If we enlarge 2 times, the result will be bigger square, which consists of 4 identical squares. The same is the result if we have a triangle as the initial figure. Now, let's take a cube. It's a 3-dimensional figure. If we enlarge 2 times, the result will be bigger square, which consists of 8 identical squares. These 3 examples shows clearly outlined regularity. The dimension equals to logarithm n over logarithm e, where n is the number of the resultant figures and e is the enlargement. Now let's apply this formula to one of the most widespread fractals. It is the Koch curve. Let's look at it. If we enlarge it 3 times, the result will be bigger Koch curve, which consists of 4 identical curves, in blue, in green, in orange, and in purple. So, the resultant figures are 4, and the enlargement is 3. So we can reach our dimension, and it is logarithm 4 over logarithm 3, and it's about 1.26. Again, not an exact dimension. There are other approaches to calculating dimension. The second method is the so-called geometrical method. The previous method, the similarity method, is very effective in calculating the dimension of fractals that are set over self-similar patterns. But if we try to apply it to the coastline of England, for example, it would be an impossible task. The problem is that in this case, all the lines have different size, so they require different magnification. There is a simple way to tackle this. As we know, a natural fractal consists of infinite number of new details. So, a fractal consists of infinite number of new details. So, we can see the difference in the size of our fractals with every new magnification. Let's take the charts below as an example. In the first, we have 3 examples of non-fractals, a cylinder, a triangle, and a segment length. While in the second one, we have 3 examples of fractals, Minkowski sausage, box fractal, and Koch curve. Now, let's draw a chart of the logarithm of the size over the logarithm of the magnification. The result in the first chart are these horizontal lines. This proves that the size of our non-fractal do not change, and this really proves that they are non-fractals. If we do the same in the second chart, the result are non-horizontal lines. This proves that the size of our fractals changes with the additional details, and this really proves that these figures are fractals. So, we can reach our dimension, and it is the inclination in this chart plus 1. Let's consider fractals in geometry and the principle of reverse connection. One of the best examples of a simple process with a complex development is a process defined by the quadratic equation of the type x squared plus c, where c is a constant. In some cases, it can be non-fixed constant, as in the case with Mandelbrot set. The reverse connection processes are fundamental in all sciences. They were first introduced by Newton and Leibniz 300 years ago under the form of laws of dynamics. Nowadays, they help us determine the position and the velocity of a particle at a particular moment using the data from the preceding moment. By using the quadratic equation of the type x squared plus c and completing numerous modifications and iterations, we have come to some of the most popular fractal constructions. Here we can see some of them. Exactly, by using this algorithm and with the help of computer programs, we produce one of the most widespread constructions. The first one, it is the Mandelbrot set. Actually, these complex fractal constructions reminds us of some geometrical figures. The cardioid is well known from many fractal patterns. It is the cardioid that is the first and the largest element in the Mandelbrot set. The cardioid in geometry can be described as a plane curve with a single cusp. It can be also described as a curve which is traced by a point on the perimeter of a circle with radius a, which is rolling around a fixed circle of the same radius. The concept of the iteratives of the identical structures, which form figures that are self-similar to the initial ones, can be illustrated in math tasks for young children. The process of learning starts with the basic of the complex processes. On this basis, it becomes easier to conceive the complexity in any process. Let's start with problem 1. The figure below consists of a sequence of attached houses. In each house, the area of the roof is 4 times smaller than the area of the square. The area of the square of each new house is twice as large as the area of the roof of the preceding house. A. If the area of the initial house is 80 square centimeters, what is the side of the square of the initial house and the area of the fourth house? If the area of the initial house is 1,280 square centimeters, how many times is the area of the ninth house smaller than the area of the initial house? I'm not going to describe the solution of this problem in details because it's easy, it's for young children. The most important thing that we should notice is that every new house has an area 2 times smaller than the area of the preceding one. So, our houses are similar with a similarity factor equal to square root of 2. The second important thing about this problem is that even it's for young children, it demonstrates a method of constructing the Pythagorean tree, a fractal, which we are going to discuss later. The solutions of the next few problems will lead to some fractal constructions. So, we are going to do our first steps in modeling fractals. Problem 2 is connected with the French mathematician Paul Lévy, namely with his fractal, Lévy's dragon. Start with an isosceles right triangle L0. Replace this triangle with 2 isosceles right triangles, so that the hypotenuse of each new triangle lies on one of the equal sides of the old triangle. Place each new triangle so that it points out from the original triangle to get L1. For the next step, repeat the process on each of the triangles that make up L1. Iterate the above procedure 4 times and compare the area of L0 with the area of L4. Here we can see the process of constructing this fractal. We begin with a right isosceles triangle, then replace it by 2 new isosceles right triangles. Actually, the area of each of these triangles is 1/2 of the area of the preceding one. In the next step, we repeat this process and replace these new triangles with 4 identical triangles to them. But again, the sum of the areas of a triangles in black is the same as the sum of the areas of a triangles in gray. So, the same as the area of our initial triangle. After the 4th iteration of this procedure, the result is the so-called Lévy dragon, but again the whole area remains the same. We can describe this process in a different way. For example, let's put in a coordination system a triangle with base 1 and sides 1/2 and 1/2, and then by homotety make a new triangle similar to it, with the similarity factor equal to 1 / square root of 2. Then, if we turn this triangle 45 degrees clockwise and translate it on the side of our initial triangle, it occupies its first position. And if we turn it 45 degrees anti-clockwise, it occupies its second position. After many repetitions of this process, the result is this beautiful Levy dragon. In the picture, we can see that it consists of two identical copies that are corresponding to the two functions of the iterative function system. The dimension of our Levy dragon is equal to 2. That's because Levy observed that he can tile a plane only by copies of this dragon. So, our fractal is a space-filling shape. That's why its dimension is an exact dimension. We can think about the curve that is outlining our Levy dragon, and we can consider it as a new fractal, the so-called Levy curve. The process of constructing it starts with a single line segment. Then it is replaced by this L shape. These are only the sides of our isosceles right triangle. Then each of the sides are replaced by this L shape, and so on and so on. This iteration can continue an infinite number of times. Actually, the dimension of the Levy dragon is 1.93, and it closely resembles the dimension of our Levy dragon. If we put the dragon in a coordination system with grid 1/4 to 1/4, it will lie within a rectangle with height 1.25 and width 2, and it will never go beyond the borders of this rectangle. No matter how many details we add to our fractal, it will just become thicker and thicker. What is more, we can start with a different starting figure. For example, if we start with a square, the result are the Levy diamonds. The next fractal has a similar way of constructing. Start with a trapezoid C0 with a base of length 1 and the other three sides of length 1/2. Replace this trapezoid with three scale copies whose bases lie on the equal sides of the old trapezoid. Place each new trapezoid so that it points out from the original trapezoid to get C1. For the next step, repeat the process on each of the trapezoids that make up C1 to get C2. We can see that the process is similar. The difference is that we begin with a trapezoid, then replace it by three similar trapezoids to it, and so on and so on. After many iterations of this process, the result is this beautiful fractal, and it really reminds us like it is formed by numerous diamonds of a different scale. Problem 4 is connected with the Makoto's pentagram and the construction of this fractal. Starting from the beginning of a coordination system, draw a line segment of length r at an angle 36 degrees. Then turn left by 70 degrees and draw another line segment of length r. Next, turn right by 144 degrees and draw a third line segment of length r. The remaining three line segments, each of length r, are formed by making a right turn of 72 degrees followed by two left turns of 72 degrees. The end of the last line segment will be at point 10. Here we can see the process of constructing this fractal. We begin with a single line segment r, then turn it 36 degrees, then 72, 144, and so on and so on. The six straight line segments in the figure give us the basic motive for the iterative function. Each subsequent iteration is done by replacing each line segment of length r with a scaled version of this basic motive. We can reach the size of our r, and through the following expression, it turns out to be about 0.4. Here we can see the first three iterations of this problem. Actually, we can construct the Makoto pentagram in this way, by using 6 non-overlapping copies of the same Makoto pentagram. And here, from this picture, it can be clearly seen that each of these copies is similar to the whole structure, with a similarity factor r smaller than 1. Therefore, we can reach our dimension. We can order 5 non-overlapping copies of the same Makoto pentagram in this way, and the result is the second form of the Makoto pentagram. If we start with different starting angles, not 36 degrees as in our case, the result are some beautiful fractal formations that really resembles objects from nature. The next problem is connected with the construction of the Pythagorean tree. Begin with a square. Construct a right isosceles right triangle whose hypotenuse is the top edge of the square. Construct squares along each of the two sides of the isosceles triangle. On the same drawing, repeat this construction recursively 3 times. Here we can see the process of constructing this fractal. After many iterations, the result is this beautiful tree. We can see the starting square and right isosceles triangle and how they scale with every new move. Another interesting thing about this problem is the crown of our tree. It really resembles one fractal that we've already discussed. Can you recognize it? It's the Levy dragon. We can make some variations in our crown. For example, if we start with a square and a right triangle but with different angles at the base. Let's start with 60 degrees and 30 degrees. The result is this variation in the crown. We can make some differences in the stable of our tree, but again the whole shape remains the same. Moreover, if we put our fractal in a coordination system with grid 1/2 to 1/2, it will lie within a rectangle with height 4 and width 6, and it will never go beyond the borders of this rectangle, no matter how many details we add to our fractal. Let's play with numbers. Take a Pythagorean tree. Suppose you number the squares only. The initial square is labeled with index 1. If a square has a label n, and the right isosceles triangle is placed on top of this square so that two new squares are constructed on it, then the new square on the left will have index 2n, and the new square on the right will have index 2n plus 1. Number the squares only on the Pythagorean tree as shown below in 4 iterations. At each iteration, call the left square with index 2n in red and the right square with index 2n plus 1 in blue. This is the result after following the steps in the text. The figure only shows the first 4 iterations. After that, the squares will just begin to overlap, but the indexing algorithm will still apply as more iterations are done. Once a square is given a particular number, it will never change, while additional squares are created. Now let's make things harder. Take a Pythagorean tree with 4 iterations. Where would square with number 45 be located? If we express 45 as sum of powers of 2, it will be 1 plus 4 plus 8 plus 32. So it will be 2 to the power of 0 plus 2 to the power of 2 plus 2 to the power of 3 plus 2 to the power of 5. We will write it in binary, and we will have 1 for the powers that we have in our expression and 0 for the missing powers. So we have 0 for the missing power 2 to the power of 1 and 0 for the missing power 2 to the power of 4. Now let's make this numeration. Let's look at the binary code. It's 101, 101. The most left digit will always be 1, and it will correspond to our initial square. Then we will have 0 for turn to left and 1 for turn to right. Let's follow the steps. Turn to left, to right, to right, to left, to right. Here is the square that we're searching for. Now let's make things even harder. Where would square root number 160 be located? If we express it in the same way and again make a binary code, it will be 1110100. Let's follow the steps. Turn to right, to right, to left, to right, to left, to left. Here is the square that we're searching for. But what about the square root number 98,156? In binary, it will have 70 digits, but we need to take 16 iterations to get to this square. Actually, the area of this square will be 256 times smaller than the area of our initial square. The figure below shows the squares with indexes 1, 2, 4, 8, and so on. We can see that they construct a spiral. Thus, we prove that our Pythagorean tree consists of infinite number of spirals. Here we can see some versions of the Pythagorean tree done in backstitch on fabric and with the Pythagoreans as the initial set. But again, the whole shape remains the same. The last problem is connected to my favorite fractal, the Jurassic Park fractal. Here I've attached some pictures of its construction. But I would like to invite you in the MathPresentation finals, where I will go into more details about this beautiful fractal. In conclusion, I consider that fractal modeling is just the first step toward gaining an understanding of the chaos in fractals which surrounds us. Indeed, by initiating chaos, we realize that it is an infinite dimension that existed long before this initiation. By fractal modeling, we improve our experience with the unpredictable. Fractals are the code which puts all seemingly chaotic systems and processes around us into motion. Thank you for your attention.
Thank you, Nia, for this excellent presentation. We still have 1 minute for questions if you like. Anybody wants to ask anything? 1 minute. Thanks again.
Thank you.